So it's my pleasure to introduce Luiz Barroso. I am not Portuguese, so he can correct my pronunciation of it. But Luiz is a vice president of engineering at Google. He manages the large Geoplatform group, which is responsible for collecting, curating the maps, imagery, local data, all of the stuff that you see in Google Search, the Geo Search, and Google Maps. His background is degrees in electrical engineering and a PhD in computer engineering from the University of Southern California. During his PhD, his doctoral research was on pioneering research in multi-core processors, which are now pretty much used everywhere, you know, like all the computers that you're using. His technical interests are pretty diverse since then, ranging from distributed system design, like the software that actually runs in data centers, to basically the design of the hardware that you can use to try to implement this type of distributed system. He has co-authored many well-cited articles on warehouse-scale computing. He co-wrote a book called The Data Center as a Computer, which was the first textbook to describe this kind of scale of making a whole warehouse into a computer, which is much different than a small cluster. And he also has had a profound work throughout the industry. He has been recognized as a fellow by the Association for Computing Machinery, the American Association for the Advancement of Science, and lastly but not leastly, he is a Google Fellow. He's one of the handful of people that have been recognized at that technical level for their contributions basically to computing in general. So please join me in welcoming Luiz.
Well, it's a real pleasure to make my sort of return appearance, I guess, for those of you who were here last year. I had a chance to chat with our own sort of Rebecca Moore here on stage, and today I will have just a few minutes to put a little bit in context what happens in the rest of our team here in Geo, of which Earth Engine and sort of this is the piece of it that we're trying to externalize and spread some of that magic, if you will, for many of us to be able to sort of innovate in this space. So we'll take a step back and just go over the infrastructure. So as sort of my introduction sort of hinted, I don't really have a business being in a sort of a geospatial field, as you can tell. I've been sort of a gearhead for most of my life, both on the software and the hardware side of things. But I think like many of you, I always had a passion for sort of understanding the world we live in, the planet we live in particular. And when a couple of years ago, there was a chance to sort of come and work with a team that was not only building those kinds of capabilities within Google, but also building the engine literally to make those capabilities available to a much broader community. It was too good of an opportunity to pass on. So I'm 2 years into my apprenticeship in almost, not quite, Kurt is nodding over there, in this area. And Earth Engine is one of these aspects of my work that is tremendously joyful, not just for the chance of actually being here every once in a while and talking to people outside of Google who are making use of this, but actually to work with the Earth Engine team itself, which many of you probably know on a first name basis by now, that a group of people that are not only technically brilliant, but tremendously engaged with the mission of spreading that kind of capability for the use cases that many of you embrace as a passion or as a profession. So it starts with machines. I spent the majority of my career at Google working on this thing we call technical infrastructure. It's just the low-level software and the hardware that runs all these things. You've seen a picture of one of our data centers. And as you can tell, our machines don't look really good, right? We don't optimize them for marketing. Since we don't sell them to anybody else, we're the only ones who have to look at them. We optimize them for serviceability. So there's nothing in front of the hardware if you need to actually go and fix something or plug or unplug a cable. But I think what this slide is mainly trying to just hint at is just the size of it. It's just, it may very well be the biggest computing system in the world if you look at it as a planetary scale. And we've been spending a lot of time learning how to build it, how to operate it reliably, and most importantly, from a user standpoint, make it seem like an easy target for programming, of which the mechanisms you currently have on your browser or on the cloud for Earth Engine, I think is an example of that, right? How do you make this sort of immensely complex machinery look to you as something that, from a programming standpoint, is sort of manageable and allows you to abstract all that complexity and get what you want sort of done. Part of what we've been doing also in the hardware side is figuring out what that hardware needs to be. We are at an age where, for those of you who sort of pay attention to the technology industry, basically CMOS and things like that, that ordinary CPUs have not been getting as fast as they used to. And at the same time, there's this whole new set of algorithms for machine learning that seems to benefit from specialized implementation of hardware just to run that one thing. So this is something that in my previous job, I began that program that's building these accelerators, if you will, for machine learning. There was a version of it that was unveiled about a year or so ago called the TPU for Tensor Processing Unit. And this is the cloud TPU. Is that the name we're giving, I think, for the second generation of this? That's the slide you're seeing right now. What that boils down to is the following. Think of a board with 4 of these chips there, which is the second version of our chips that accelerate deep learning style machine learning algorithms, right? And imagine sort of a board like this being equivalent of something in the order of a quarter of this row of sort of computing equipment, right? Now imagine that of regular standard general purpose, processors as you know it, right? Now imagine the gains that that gives you, not just in terms of cost, in terms of energy usage, of course, right? But most importantly, capabilities. We're able to actually do things with these things that we weren't able to do before. Those of you who are beginning to or have been playing with machine learning for a while understand that a lot of the innovation cycle for machine learning is bottlenecked by the time it takes to train a new model to do a thing. Once you've trained the model, you are in pretty good shape, right? Then you can run inferences and ask questions of the model. But that process of training is very laborious. And this TPU system here is particularly targeted at speeding up that training process, which is basically, if we believe that we're all in the innovation business, speed of iterating on innovation is really key for it. And that's what this kind of hardware capability allows us to do. Now, one of the things that this thing does as well is do things that, some people consider superhuman, right? Beating the best players in the world in the game of Go, which is something that people imagine would only happen, a decade or 2 from now, given the complexity involved in this game and the capabilities of computers as we know them. And this is a really, and for those of you who don't know, there's a computer that was built with the previous generation of this chip here, right? That was the first one to build a world-class sort of Go champion in that one game. The part that I want to highlight here is that these things are these kinds of tasks that appear superhuman, sort of, and begins to, in the minds of our science fiction colleagues, and maybe many of us, imagine machines that will have superhuman capabilities and to some extent will dwarf our cognitive capabilities, et cetera, right? I actually have a different take on this that hopefully I'll get to towards the very end of my talk. I think these things are incredibly impressive, but the benefits of the kind of machine learning technology that we have today are not as much along the lines of creating things that are superhuman. They're along the lines of scaling human things to a scale that has been impossible or economically inviable before. And that's what I think it's magic there. That's going to allow many of us to actually do things we could never do before. So let me talk a little bit about my team as a whole, with Earth Engine is a part of it. This is basically what we're trying to do, if you want to summarize it in one sentence. We want to know everything about the world, right? There's Google Search that wants to know everything about the information that exists online, right? So the virtual world, so to speak. So we are the counterpart to the regular Google search, even though we can find our information through Google search as well. But we are interested in things that exist in the real world. We're interested in knowing where all the streets are, where all the businesses are, where all the rivers are, how they change, how people move about that world, things that are intrinsically around life and the planet sort of we live in. And we keep trying to do that at the larger scale, at a larger level of detail, and then, of course, to make more of that information available to sort of many of us here. Let me give you some of the examples of the kinds of things we're able to do today with the combination of the infrastructure that I mentioned earlier today and machine learning capabilities. One of the things that's really important for us to try to understand is how quickly the world is changing, not just as a number per country, but at the micro scale, at each municipality, at each corner. Because as you can imagine, if we want to make an analogy to web search, where you have to crawl the web, right, to get all the information from all the web pages out there, and then index them and make them available for you in a web search. If we want to do the equivalent of that for the world, we have to crawl the world constantly every time, 24/7, and the world is changing constantly. So one of the ways that we are increasingly getting our geospatial data that you see through Google Maps or through local search looking more like it's an up-to-date version of the world is by cheating, right? We don't photograph and crawl and drive the entire world 24/7, every street corner. We try to find out what places are really changing, which actually, by the way web search does it too, right? The web search develops these algorithms that understands, oh, the CNN web page sort of changes pretty much every second or so. So I need to do something special for these kinds of places. Whereas my personal web page hasn't changed in probably 2 years. Right? So I probably don't, I'm sure that's the case with many of you. So this is a pictographic reference to this, where what we're doing in this is actually at a very large scale looking around movement of people. We have anonymized traces from people who enable location sharing on their phones that lets us know places that actually are sort of more populated now than they were sort of before, or there's a significant change in the movement of people around those places. And this is one hint that maybe something has changed in that place. And perhaps these should be places we should be collecting new information on or updating our information there, whether it's imagery, whether it's understanding that the business changed owners and it's no longer this restaurant, it's another restaurant. For those of you who are in the Bay Area, you know, a restaurant in Palo Alto probably lasts on average 9 months or so, right? So sort of knowing how these things change is incredibly important. And this is an example of how you can do that at a global scale, which is really exciting. So another way, I just gave you the time dimension. This is sort of a pictorial view of the space dimension, right? We actually cover something on the order of 30 million miles of the world in terms of imagery. I think that number is mostly correct, which is, you know, more than 10 times the kind of coverage we have when we began sort of this journey here. And not only that, but we keep sort of historical information, so which I know it's very important for many of you to sort of understand not only a snapshot of things, but how things change over time, especially during the times we live in, and especially if you're looking at things that relate to sustainability and conservation efforts. So that kind of scale in the spatial sense is also really impressive. And thanks to technology that we actually help nurture here at Google, as well as others in the case of sort of the satellite industry, there are ways for us to actually use combinations of this, which is sensing where things have changed, and then tasking sort of satellites to give us fresher imagery from little swaths of that place, so that we can make sure that the global picture of this planet is sort of more up to date as time sort of moves forward. So time and space sort of scaling, right, increasing the level of resolution in both ends of the spectrum is key for everything that we do in geo. The other way we acquire data is not from the sky, but from land. And there's an awful lot of information. I mean, not only these pictures are gorgeous, it allows you to experience places that are far away that you can't sort of be in for right now, but they are useful for us in all sorts of different ways as well. This is an image from our Street View sort of program. One example of that is that the combination of machine learning, again, is that a common theme in this conversation, and sort of this degree of imagery allows us to discover businesses that actually have no otherwise any online presence whatsoever. And in this example, our algorithms are actually able to take the panoramic shots from a street view camera as it drives and recognize that these are special characters that actually matters to us. This is probably a storefront. We can probably tell the title of the storefront. We could probably infer the category. We can probably tell this is not a restaurant, right? And we can probably also throw away parts of text that may not actually be as interesting, which in this photo, I don't think there isn't that much. But if you begin to look at storefronts a lot from these kinds of street view panels, like I've done, you realize that probably less than 50% of the text you can recognize in an image is actually useful, right, in terms of understanding what that business is, right? So being able to not just OCR, right, not just recognize all the text that is there, but actually tell apart what text is important, and then bring that text in a structured format to update our databases is really, really important. In particular, if we are going around places outside of the US and Europe, right, what we call sort of the next billion users, sort of, right, the people, the populations that are coming online right now. The fraction of those folks that actually have online presence is very small, and this is a way that we basically put them on the map. They can be found on Google search, right? And that has actually economic benefits from them that are very valuable. I will conclude very briefly by just showing a slide of something that many of you are familiar with, is how you can actually use Earth Engine, in this case in combination with machine learning, to actually do really amazing computations. And here's where I want to go back to my point about the real magic of machine learning. It is not necessarily, although it will do things and point places that look superhuman, like beating the world's sort of best Go player. We have examples, for example, in our machine learning team today that actually can read imagery, medical imagery, and make some kinds of diagnostics for some kinds of diseases that are actually at expert level or slightly better than the average specialist on that particular area, right? Which is really fantastic. But when you think about things like these, the real beauty of that is often not the case that it can do something it's impossible for a human to do, but it's impractical for humans to do at scale. It's impractical to ask every optometrist or every physician in the world to be at the expert level at these simple tests at reading a sample to say whether that actually has cancer or not. But you can amplify the knowledge of that expert and scale it to a point that it's available to a much larger population. That is the magic of machine learning. It's not the superhuman capability, it's really scaling the human capability to then resolve sort of problems that are completely impractical for us to do by hand. I mean, the kinds of things we do today at the planetary scale within sort of our Geo platform team for Google's products often have that kind of flavor. We know now, that, for example, that in this one particular street, you no longer can make a left turn. You have to go straight. Now, a human could be sitting on every intersection in the world giving us that data right immediately. But our machine learning systems, looking at the movement of cars around the world, can deduce these things automatically. Again, we're not doing something that's superhuman. We're scaling a human capability to create something that's really remarkable. So, and I believe that a lot of the things that are going to be really remarkable about Earth Engine will be sort of along those lines. And I'm very excited to seeing what all of you will continue to do with this sort of amazing tool. And with that, I will stop, and I will be happy to talk about any of this.
Thank you very much for your presentation. I have a question. Actually, like I believe Google contribute a lot of like the Google Map, like a GPS navigation, that is help us to reduce fuel consumption of car a lot, I believe. But on the other hand, like Google server use electric consumed by the many kind of like fuels.
Yeah.
Do you know any like a balance? I believe like a Google kind of reduce the fuel consumption of the car based on the navigation system. But what do you think about the balance between the server,
the energy we use versus the energy we save elsewhere?
Yeah, do you have any idea for it?
That's a great question. I don't have actually a global number to give you, especially because it's difficult to look at that as just kind of a zero-sum game in the sense that computing capabilities just allow things to happen that never existed before. So we have nothing, no baseline to compare against, right? I can tell you sort of a few things that are really, really important for us, for example, right? And that hints at what you're saying. We allow different kinds of electronic communications, from audio to video conferencing, for example, that actually prevents people from actually traveling. I use that a lot, right, to talk to my colleagues sort of across the world, for example. And that's kind of important. I think that that's important sort of for everyone involved. There's the, there've been, if you go to sort of, we have a web page on sustainability at Google. I forget what the exact URL is.
Environment.google.
Environment.google. Thank you, Rebecca. It'll give you a lot more information about the kinds of places where computing capabilities actually have an enormous net impact on sustainability. There is a study that was done 3-4 years ago. It's called 2020 or 2030. It's a study that actually was done trying to understand not Google, but how computing technology's net effect on the overall savings of energy across the world is already enormous and is going to become even bigger. The anecdotal example I have for you is the following. In a city just outside Washington, D.C., 4 years ago, this computer that just, the only job it did was in the 2 main thoroughfares of this street, control the timing of the lights, right, the traffic lights, to sort of, to change between morning and afternoon to adapt to sort of daily commuting patterns. That computer crashed. Happened to be an old digital equipment computer that has been sitting for a long time, so people actually took a long time to figure out how to replace it. During the time that this happened, a city that had sort of heavy traffic, but overall sort of manageable, came to a halt. People actually couldn't get anywhere in that town. And all the lights were working, but they just went to their sort of self-dumb mode, where they were just on for a while, and green for a while, and red for a while, right? So the ways in which computer capabilities in general are right now already making so many of the things we do much more efficient, and in particular energy efficient, is a calculation that I think would be wonderful to do it every once in a while. And the ones that I've seen so far, even though they are wildly sort of inaccurate, they're enough to tell us that there's more than an order of magnitude cost benefit sort of across the board for many of these things we do. And that's not to mention the efforts that we have done ourselves at Google at making sure that our own energy budget is not only primarily green energy by investing in building actually solar and wind generation farms, but also in the computing side, reducing the energy usage of sort of all of this. And this happens to be an area that I can bore you to death because I worked on the electronics of energy efficiency here at Google for many, many years. So I'm happy to tell you a bit more about that.
Hi, so my name is Solomon, and I come from the catastrophe risk modeling domain. So what I'm most interested in is data, right? So in Google Street View, you have information on building fronts and also the level of the building. So for flood modeling, what you need the most is where the building starts. So then when you model the flood, you know at what point the damage is going to increase, right? So do you think at any point that sort of information would be available to Earth Engine users? And for example, it could be used to improve the quality of DEMs, for example.
Yeah.
And that is applicable to a lot of science domains. Do you think that sort of data is going to be available to?
Yeah, I think it's quite possible. Certainly, it's very possible that we'll make that available as a commercial offering for sure, right? Part of what we're trying to do with this is that is to make sure that in sort of every domain where people can take advantage of this kind of information, that information is actually sort of being made available to them in a way that can actually responsibly sort of use that. And that means sort of the accuracy and the timeliness sort of all of this, as well as actually having the serving capability to serve all the bits to do that. My current preference in this area from if I put my computing infrastructure sort of hat on, right, is that doing it in a way that exports a ton of imagery sort of outside of Google through some kind of RPC system is the most inefficient way possible of doing that, right? You want to do a significant amount of data reduction inside of our data centers. So we keep looking at ways of making sure that these kinds of capabilities are made available sort of inside our cloud, and Earth Engine sort of is a key part of that. I think it's more likely, in part because I think it's actually the more useful way of doing things, that we begin to understand what kinds of features of buildings, for example, that will be of wide interest sort of across the industry. And instead of actually asking you to do sort of all of that work, we have pretty good people in machine learning. We have super good quality sort of imagery to begin with. We have computer vision specialists that know how to pose that imagery very accurately. It's more likely that we'll create these rich annotations. And we'll give you what you actually want, right? Because you don't necessarily, at the end of the day, want the pixels. You want the information that's extracted from them. That is the direction I think that we are going to go.
Yeah. For example, if FEMA wants to start using that sort of information for improving their flood models, to improve their flood insurance for citizens, at that point, what is Google's policy to share that sort of data? It's always
we have been, especially in situations like FEMA and government agencies and nonprofits, we've always erred on the side of actually making sort of these services that otherwise would charge businesses for available for them for a nominal fee or free. So this is sort of not a promise on my side, but that is what our past behavior sort of has been sort of in these general areas. In fact, there's a group right now that's looking precisely at that sort of here at Google, at how to derive good quality imagery for insurance assessments, and that's basically risk. And risk is something you obviously sort of care about in many ways, right? So I wouldn't be surprised if things like that actually were made available as well. So the intent, as you've seen, is for the catalog of information that's available in Earth imagery to grow and grow and grow over time, right? And we need to balance that with the cost that incurs for us to actually collect all that information, right? And making sure that we have a commercial sort of viable business that we can sort of continue to support, things like Earth Engine for everyone else sort of to use, while at the same time, anytime we have a good excuse for doing so, which we like to, is to actually making that available, that information available to a broader community.
I just want to ask two small points. Much of what we are looking at in machine intelligence today is to find more data from already voluminous data that is available for the whole world.
Yeah.
But what is going to be the future trend in looking at all this data, not just for discovering more data, but for prediction of events in the future, of what will happen tomorrow in a particular place, or what will happen in the world, what will happen to the climate.
Yeah.
Where is the world going on this line for this? Because that is what is of interest in the analytics domain. And the second small point I want to ask is, while much of the machine intelligence things that we are talking of today, the humans are being rid of doing many of those repetitive tasks, what will the humans do 25 years down the line? And what will be the type of geospatial data 25 years down the line? Is Google doing something to model that?
I don't know the answer to your very, very last question, and I'll try to sort of get to those sort of in order, if I remember correctly. The prediction thing is fascinating, right? And the difficult thing for us to do is that you probably met everyone that works on Earth Engine here sort of the past day, right? This is not a large team. The way we're going to win these kinds of games is by creating a developer community where people that have domain-specific knowledge in an area, they know how to model that particular phenomena, whether it is water usage, melting of glaciers, weather, animal population, right? We want to actually create that engine to empower those users, and we'll hope that those users, as they do, often actually share those models with the rest of the community. So I think that's the only way for us to attack the prediction side of things, because there's just an enormous surface of this, right? So we want to create the basic data infrastructure. We want to actually create the ecosystem that allows sort of many of you to share your prediction models sort of with each other, and have that happen sort of, you know, in that way. Get to your second, oh yeah, what people, yes, yeah. So, you know, I think it's a puzzle for actually all of us, and I think it's a really serious question. I don't think that that's one that I can or anybody can easily dismiss, especially because there's a history of it, right? When the, you know, Industrial Revolution happened in the sort of, I don't know, early 1800s, many cities in England went destitute, right? That did happen, right? So I think it's something, you know, the world didn't end as well, right? And that's like the second part of this, right? There were different ways in which sort of education levels sort of ran across the board. People's cognitive abilities remain sort of very interesting and very useful, right? So my hope, and actually that's something that Google invests in as part of our social responsibility pillars, is that there'll be enough in the way of both government and private investment on continuing to up-level what humans can do in terms of basic education in such a way that there will still be more than plenty sort of interesting things to do for people. They will stop doing things that sort of machines are better off. It's a continuation of a process that's been going on for millennia. That process is always a little disruptive. This, I think, is going to be another one of those bumps sort of on the road. But, you know, we see this in our internal teams that deal with this information, right? Our operations staff, for example, they do things today that they didn't do 2-3 years ago because machines took on some of those jobs. The number of people employed in our operations actually has not decreased so far. I mean, that could happen, right? But I'm certainly sure it's not going to go down to zero. And in part it's because there's still tons of problems to be solved. And if you believe my premise that the superhuman sort of machine is going to be a few rare, you know, eye-popping sort of headline events in a newspaper, but the real impact is scaling things that humans can actually sort of do, I think that there's a lot of still left in our cognitive system that is of value that machines are not going to be taking on sort of anytime soon. I say that from somebody who is more of an expert in the underlying circuit technology. That is the basis for sort of all of this thing. I think there's a degree of unhealthy enthusiasm sort of at times for the fringe sort of vision of you know, robot overlords, you know, in 2020. I like soccer. I still want human beings to be playing football in World Cups in 2030. So I'm looking forward to that. Thank you very much.
Well, thank you. Thank you for the wonderful presentation.